Welcome to this constraint programming course. What is constraint programming? Let's first answer to that question. So some people consider that constraint programming represents one of the closest approach we ever have met in computer science. This is one approach that is very close to the holy grail of programming. It means that the user states the problem and the computer solves it. And so by stating the problem, you may ask, what do you mean exactly? Is it stating the problem like in your head, and then you press the button and magically you find a solution? Not yet, but this may be the future. We don't know. By stating the problem, I rather mean declarative programming. Declarative programming is a programming paradigm that expresses the logic but not the computation itself. You express the logic and the properties that needs to be satisfied by the solution, but what you want to program, by the output of the program. And so in constraint programming, what you want to solve is a combinatorial optimization problem. And so what you will express is the properties that needs to be satisfied by the solution you want to discover. And then you press the button by asking the constraint programming solver, can you please find a solution that satisfies all these constraints that I asked you to satisfy? Let's take one counterexample of what is not declarative programming. What is not declarative programming is a program like this one. This one is a Python program. And you can see that in this Python program, I'm really using for loops, recursive programming, and so on. And so this is really a kind of algorithm. So it's not at all declarative programming. I'm not stating at a high level way what are the properties that need to be satisfied. And so if you really want to understand this program, you really need to understand the algorithm. So this is not declarative at all. On the other side, I will show you something that is very declarative. For instance, this is very declarative. I'm using here a library that is called a numberjack, which is also a library in Python. And in this program, I'm also using this library to solve a Sudoku problem. And because I'm importing this library, I'm able to state high-level properties of the program like this. You see that here I'm declaring a matrix variable, and then I'm declaring the rules of the Sudoku, all different on the rows, all different on the columns, and then for every block I say that the values must take different values as well. So this is really all the rules of a Sudoku problem. And then here I'm pressing the run button. I ask to the constraint programming solver, please find a solution that satisfies all this set of constraints. And this is really declarative programming, very high level. You don't have to understand how the solver will find a solution here. You just need to understand how to state the problem, how to state the constraints. And this is why the CP mantra is this one. Is constraint programming is all about model. So model is really important. And then you also have the search. The search is the process that you use to discover the solution. So this is more an algorithmic part. And in modern constraint programming solver, I put this in parentheses because most of the time you don't have to really understand this part. You can only focus on the modeling part. But for advanced users, this might also be important to understand how to program the search to discover a solution that will exploit the model and all the constraints. So this is really the high-level user API that you use for stating the declarative program, so stating the constraint programs. The model will make use of variables, and each variable will use domains. And domains represent the set of possible values for every variable. For instance, this is one variable, x, and you say that x must take one value which is either 5 or 9 or 10. Okay? And so this is what we call the domain. Usually we represent it as d of x. For the constraints, they will link different types of variables or different variables. And you can have arithmetic constraints, you can have logical constraints, and you can have combinatorial constraints such as this one. Let's study one example of a model that looks a little bit like a real problem. You know the traveling salesman problem. I'm sure you know it. Okay. This is a version of the traveling salesman problem where you have a vessel, and the vessel should visit one city after each other, and you cannot come back. So you cannot do this and then come back here. Okay, you cannot do that. So you should really discover what we call a Hamiltonian circuit that visits every city exactly once, and then you come back at the beginning, and you want to discover the shortest possible circuit. How to model this problem? One possible model is this one. You will introduce one variable for every city, like this one, and the domain of this variable will represent the next city that you may visit just after. So initially you may visit all the different cities. From here you could go there, there, there. Okay, you don't know which one. But of course you want to prevent the self loop. And so to prevent the self loop, here you see that I didn't add the value I, it's the domain of xi. Okay, but for the rest you don't know yet. So this is why initially in the domain of this variable you said that every possible city is a possible successor of another city. Inside the constraint programming solver, we may want to use many different types of constraints. And so you should view a solver as a set of Lego game. And then you can just pick one constraint. For instance, I take all different constraints, you take it and you use it for your model. And so a library of a constraint programming solver is composed of many different constraints that you can really assemble to create your model. And this is why this is very high level. It's a little bit like playing Lego. You take the Lego bricks, you assemble them on the domains, on the variables, and then you press the button and discover a solution that implements the Lego specification. And so by using the Lego bricks, you give solvers as much as information as possible on the kind of solution that you are looking for. What problem can we solve with constraint programming? We can solve combinatorial optimization problems, and this is a broad class of problems. So I already gave one example, which is Sudoku. Sudoku is a combinatorial problem. Okay, it's a discrete problem, and if you want to enumerate every possible solution of this problem, this is huge. You have an exponential possible number of solutions, and so the search space is also huge. But there are many industrial problems that satisfy these requirements. You have, for instance, scheduling problems where you want to organize a set of activities or a set of tasks, and every task consumes a set of resources. This is scheduling problems. You also have routing problem. Routing problem is, for instance, the traveling salesman problem is a routing problem, but you may have more complex problems involving several vehicles, involving several types of customers, involving capacity in the trucks, and this kind of constraints. You also have rostering problems. Rostering problems, for instance, is you want to create a schedule for the university. When should you schedule every exam such that the capacity of the rooms is sufficient, the professors are available, you don't have conflicts. So for instance, you don't have to pass my exam in the same time as the exam of another colleague of mine, for instance. So many types of constraints. We call this kind of problem rostering problems. And so these three families of problems are also combinatorial optimization problems that you can tackle with constraint programming. So let's take, for instance, the job shop problem, which is a scheduling problems. You have a set of jobs here, and a job is composed of activities. So for instance, this activity must precede that one, that must precede that one, and so on. So every job has a linear precedence constraint, but you see that every activity has a specific color here. And the color represents the resource. And the constraint of this problem is that not two activity with the same color can overlap in time. For instance, let's take this one, the green one. You see that it's not scheduled at the same time as the other green one. They do not overlap in time. And so to prevent that, I will use a specific type of Lego constraint, which is called the disjunctive constraint. And then this disjunctive constraint will simply enforce this, that the execution time of the activities do not overlap in time. So constraint programming is really declarative. You can create declarative models because you have a rich modeling language at your disposal. It's very flexible. You can also program the search if you want. It's also very reusable, and it's also extensible. Assume, for instance, that one of the Lego brick is missing. Then you can just decide to implement this Lego brick, and so you would extend the solver so that you have this new Lego brick that is available for you. I already mentioned variables such as integer variables. For instance, x belongs to 1, 2, 3. But we also have other types of constraints and other types of variables in constraint programming. You can have set constraints, set variables, graph variables, and also bit vector variables and whatever. So it's really a framework that you can extend, and it's not limited by, only limited by your imagination, actually. What are the closest technology that is available that you already have studied in other courses? For instance, mathematical programming. You probably know mathematical programming or mixed integer linear programs. Okay, and so for mixed integer linear programs, it's also highly declarative, but there is a limitation compared to constraint programming is that all the constraints must be linear and the objective function must also be linear. And so if you want to model your problem, your traveling salesman problem with this, you would model it like this with binary variables. And so you have a variable xij, which is a 0-1 variable to say if you take the edge, for instance, between 2 and 4, if you put it in your model or not. Of course, the incidence to every node must be at most 2 inside a circuit. And you also have this constraint to prevent any sub-circuit in your solution. And so, of course, there is an exponential number of this one, so it's quite heavy. It's a quite heavy model. But if you want to declare the traveling salesman problem in a declarative way, this is what you should do if you restrict yourself with linear constraints. In constraint programming, you can use a richer language to state the constraints. And in particular here, you can really use the circuit constraint, which is one building block that is available to say, I want a Hamiltonian circuit. And so you see that this model is much more readable, I would say, compared to this one, which is a little more advanced in terms of mathematical programming. And in constraint programming, you can also have optimization, and you can minimize a specific objective function as well as you can do it in mathematical programming as well. Okay, in the next part, I will explain a little bit more how the discovery of the solution is done inside the constraint programming solver.